Now we will learn about the combustion theory, how the combustion happens in the IC engine. Very first, we'll learn about the combustion in SI engine. Now, before learning the combustion concept in the SI engine, we should know few terms. So, first is the ignition limit. Ignition limit corresponds approximately to that mixture ratio at lean and rich ends of the scale, where the heat released by spark is no longer sufficient to initiate combustion in the neighboring unburnt mixture. The flame will propagate only if the temperature of the burned gases exceeds approximately above the 1250 degrees Celsius. In the case of hydrocarbon air mixture, the lower and upper ignition limit of the mixture depend upon mixture ratio and the flame temperature. The ignition limits are wider at increased temperature because of higher rates of reaction. So, in case of SI engine, we may observe these are the ignition limit. So, here on this scale, the air fuel ratio is mentioned, and if we check the 0 to 7 air fuel mixture, it is too rich mixture where only 7 molecule of air and 1 molecule of fuel. It is too rich mixture 9. Then 14.5 is this the chemically correct air fuel ratio or the stoichiometric air fuel ratio 21:30. Beyond 30, it is too lean mixture. So the ignition limit where the ignition can happen, where the proper combustion can happen is from 7 to 30. This is the ignition limit of the hydrocarbon. Now practical limit of the carbureted engine is from 9 to 21. Beyond this the carbureted engine cannot work. Now we'll learn all the stages involved in the combustion of SI engine. Very important point. So if we check, this is the pressure versus crank angle diagram drawn to show the stages of combustion. Here we'll see that stage 1 is the ignition lag, stage 2 is the flame propagation, and stage 3 is the afterburning stage. If we check here, the crank angle that is approximately 15 to 20 degree before the top dead center. Here, this is the compression where the pressure is rising A to B. This is the region. Here, the pressure is rising and the maximum pressure of compression is here shown. It is shown. It is up to 25 to 26 bars. So, stage 1 is the ignition lag where the pressure is just rising but there is no initiation of the combustion, no ignition happen. At point B, here we may observe the pressure is up to 8 bar. Okay, this is stage 1. Now what is the stage 2? Propagation of the flame. Once the ignition happen, the flame start propagating in the combustion chamber. There is rise of pressure is observed up to 26 bar. From 8 bar to 26 bar pressure rises. Here the flame propagate in the combustion chamber and now the flame reaches to the end and the combustion happen properly. And from C on the third stage, that is we may see the flame propagation happen from 8 degree before TDC to around 12 to 15 degree after the TDC. After that, from point C onwards, C to D is the afterburning phase where the burning is still continuous but the expansion stroke already over and exhaust stroke is started. So the pressure is reduced drastically here and this is the third stage of combustion, that is after burning. So this is the normal combustion in case of SI engine. Here the same thing is explained here where the stages of combustions are explained. So it is a chemical process. Ignition lag is actually the chemical process. It depends on the nature of fuel, the temperature and pressure available in the combustion chamber, the proportion of the percentage or we may say the proportion of the exhaust gases, rate of burning at the temperature. It is the ignition lag, it is nothing but it is also known as the preparation phase where it is the growth and development of semi-propagating nucleus of flame. At the moment of the spark discharge, the temperature exceeds 1000 degrees Celsius. At the end of this stage, the first rise of pressure can be detected. Pressure is slightly rises. It is the point where the line of combustion departs from the compression line. Now the second stage, that is flame propagation, it is a simple pure mechanical process. The starting point at the second stage is where first measurable rise of pressure can be seen on the indicator diagram. That is the point where the line of combustion depart from the compression line. We may observe here. This is the point, start of the flame propagation, and it rises above this. During second stage, the flame spread throughout the combustion chamber. Complete combustion chamber is occupied by the flame. The second stage end as maximum pressure on the indicator diagram. So maximum pressure we have observed up to 26 bar is achieved. Now the third stage after burning, it is the end of second stage, means completion of flame travel, but it does not result in complete heat release or the burning of the fuel. Even after the passage of flame, some chemical adjustment continue throughout the expansion stroke near the wall and behind the turbulent flame front. The rate of combustion reduces due to surface of the flame front becoming smaller and reduction in turbulence. Now, what are the effect of engine variables on the ignition lag? Ignition lag, as we know, it is a chemical process. The ignition lag in terms of crank angle is 10 degree to 20 degree, and in terms of second, it is 0.0015 second. The duration of ignition lag depend on number one, fuel. It is depend on the chemical nature of fuel. The higher the self-ignition temperature of fuel, the lower the ignition lag. Mixture ratio. The ignition lag is smallest for the mixture ratio, which gives the maximum temperature. This mixture ratio is somewhat richer than the stoichiometric ratio. Initial pressure and temperature. Increasing the intake temperature, pressure, or the compression ratio, and by reducing the spark, retarding the spark, it all reduces the ignition lag. Electrode gap. Electrode gap affects establishment of nucleus of flame. If the gap is very small, quenching of the flame nucleus may occur, and the air fuel ratio for the development of flame nucleus is reduced. Turbulence. Measured in degree of crank rotation, the ignition lag increases almost linearly with the engine speed. For this reason, it becomes necessary to advance the spark timing at higher speed. Excessive turbulence of the mixture in the area of spark plug is harmful since it increases the heat transfer from the combustion zone and leads to unstable development of the nucleus flame. That is that is why the spark plug is usually arranged in small recesses in the wall of the combustion chamber. Now we'll learn the effect of engine variable on the flame propagation, that is stage 2 of the combustion. First is fuel air ratio. With hydrocarbon fuels, the maximum flame velocities occur when mixture strength is 110% of the stoichiometric air fuel ratio. Lean mixtures release less thermal energy, resulting in lower flame temperature and flame speed. Very rich mixtures have incomplete combustion. Some carbon only burns and carbon monoxide and not to CO2, which result in production of less thermal energy and hence flame speed is again low. Now the second parameter is compression ratio. A higher compression ratio increases the pressure and temperature of the working mixture and decreases the concentration of residual gases. High pressures and temperature of the compressed mixture also speed up the second phase of combustion. Total ignition angle is reduced. Maximum pressure are increased. Intake temperature and pressure increase in the intake temperature and pressure increase the flame speed. Now we'll see the engine load. With increase in the engine load, the cycle pressure increases and the flame speed also increases. Turbulence. The flame speed is very low in non-turbulent mixture. To have the very good flame propagation, the mixture should be turbulent. A turbulent motion of the mixture intensifies the process of heat transfer and mixing of the burnt and unburnt portion in the flame pot. These two factors cause the velocity of turbulent flame to increase practically. In proportion to the turbulent velocity, however, excessive turbulence is also undesirable. Engine speed. With the speed increase, the turbulence of the engine also increases. So, therefore, the turbulence and the flame speed are actually linearly varies with the engine speed. The crank angle required for the flame propagation, which is the main phase of combustion, will remain almost constant at all speed. Engine size. Engine of similar design generally run at the same piston speed. This is achieved by smaller engine having larger RPM and larger engine having smaller RPM. Due to the same piston speed, the inlet velocity, the degree of turbulence, and the flame speed are nearly same in similar engine regardless of engine size. That is, the number of crank degrees required for flame travel will be about the same irrespective of engine size provided the engines are similar. Now abnormal combustion we'll see in next class.